Logarithmic Differentiation, Part 5. Okay, let's compare the following three functions. So we have a y is equal to x squared, I suppose a different y is equal to 2 to the x, and an even different third y is equal to x to the x. So if we look at this first function, this y is equal to x squared, we have a variable which we can think of as a function itself. So we have a function raised to a constant. And then for this next one, this y is equal to 2x, we have a constant raised to a variable, or raised to a function. And then for this last one, x to the x, we have a function raised to a function. We know how to take the derivative of these. We know how to take the derivative of these. But before logarithmic differentiation, we didn't have a way to take the derivative of these. Because we don't know the derivative of an x to an x. We know what to do if we have an x squared, and we know what to do if we have a constant to an x. So we know how to deal with powers, and we know how to deal with exponential functions. But this, we don't even really give a specific name. We have a function to a function. So let's look at what to do when that happens. So we have y is equal to x plus 2 to the x. This is one function raised to the power of another function. So what we'll do is we'll take the natural log of both sides. So we have the natural log of y is equal to the natural log of x plus 2 to the x power. And then we can use log rules to simplify this. So we have the natural log of y is equal to x times the natural log of x plus 2. And this is something we can actually deal with. When we had this, we didn't have a way to take that derivative. There's no product rule or quotient rule for that. We were just stuck. There's not even like a gross time-consuming way to do this. I suppose we have the definition of a derivative, but even that is just kind of awful. So instead, we need to use logarithmic differentiation for a function to a function. And now when we look at this, we have a product. And that's not too bad. We just have this one product rule we'll have to use here with a little bit of chain rule for the natural log function. So let's use our product rule real quick as we take our derivative implicitly. So we have 1 over y dy dx is equal to the first function, x, times the derivative of the second function. The derivative of natural log of x plus 2 will be 1 over x plus 2 times the derivative of x plus 2, which is actually 1. So that's the first piece of our product rule. So first function times derivative of second function. Now we need our second function, so natural log of x plus 2, times the derivative of the first function. The derivative of x is 1. Then we'll need to multiply both sides by y. So we have dy dx is equal to x over x plus 2. That's just multiplying my x there, plus the natural log of x plus 2 times y, but I know what y is. Y is x plus 2 to the x, so I can substitute that in. So that just comes from multiplying, wait, I wanted you to be orange, multiplying both sides by y. And that is our derivative, which we couldn't have found unless we took the natural log of both sides. Next up, we have y is equal to cosine of x to the sine of x. So this is a function raised to the power of another function. So we have to use logarithmic differentiation. So we have the natural log of y is equal to the natural log of cosine of x to the sine of x. And now we can use properties of logarithms to simplify that. So we have the natural log of y is equal to, well, the exponent inside that logarithmic function, if we want some extra parentheses here, is sine of x. So we can pull that out. And we have sine of x, natural log of cosine of x, which looks much better, and we can actually take the derivative of this. We will, however, have a product. So we'll need to use product rule as we take this derivative. So the derivative of the natural log of y, which has a little extra bump there, is 1 over y dy dx using implicit differentiation. And then product rule, we have our first function, sine of x, times the derivative of our second function. The derivative of natural log is 1 over what's inside of it, so 1 over cosine of x. And the derivative of cosine of x is negative sine of x. So we just used some chain rule there. Continuing our product rule, we have our first times the derivative of the second. Now we need the second, so natural log of cosine of x, times the derivative of the first. The derivative of sine of x is cosine of x. And we just have to be really careful here. This cosine of x is inside of this natural log of x. This cosine of x is multiplying the natural log of cosine of x. So that isn't a cosine of x squared, because one of our cosine of x's is inside a natural log, and one of our cosine of x's is outside our natural log. Okay, now we need to multiply both sides by y. So we have dy dx is equal to sine of x over cosine of x gives us tangent x. So we have negative sine of x tangent x. We also could have written this as negative sine squared of x over cosine of x. Plus, let's put that cosine of x out front so it's a little more clear that we have a cosine of x times a natural log of cosine of x. And then we multiply both sides by y, but we know what y is. Y is cosine of x to the sine of x, so we can substitute that in for the y. So that means, I didn't actually mean to erase that, that we're multiplying by cosine of x. My cosine to the sine of x. And that is our derivative. Now this guy is a little bit tricky. Notice that we have these parentheses all around this natural log of x. That means that this entire natural log of x is being raised to that x squared power. So we have to be careful because natural log of x raised to the x squared power is not the same thing as the natural log of x raised to the x squared power. So these aren't quite the same thing. And often we'll write that like this. So these aren't the same thing either. This entire natural log is being raised to the x squared power. So if we want to deal with this function raised to the power of another function, we have to use logarithmic differentiation. So we're about to take the natural log of a natural log, and we'll have to be very careful as we keep track of this. So we have the natural log of y is equal to the natural log of the natural log of x raised to the x squared power. Now, this exponent is inside of a natural log function. So we have that the natural log of y is equal to x squared times the natural log of the natural log of x. So we have a natural log inside of our natural log. And now we can take the derivative, because we don't have any functions raised to functions. We do, however, have this product, and inside right here we have some chain rule. So let's take our derivative implicitly. We have 1 over y dy dx is the derivative of the natural log of y with respect to x. And that'll be equal to, now we have to use product rule. So we have our first function, x squared, times the derivative of the second function. The derivative of natural log is 1 over what's inside of it. We have a natural log of x inside of it. So that'll be 1 over the natural log of x times the derivative of the natural log of x inside of it, which is 1 over x. So this is the first function times the derivative of the second function. Now we have to add the second function, the natural log of the natural log of x, times the derivative of the first function. The derivative of x squared is 2x. And then we can do a little bit of simplification here. X squared times 1 over x divides out one of our x's. So that's my x squared over x is equal to just x. And when I do that, both of my terms here have an x, so I can factor out an x. And I'll also multiply by this y at the same time. So I have dy dx is equal to this x that I'm pulling out times 1 over the natural log of x plus the natural log of the natural log of x. Oop, lost my 2. 2 natural log of the natural log of x. And this is all times y, but I know what y is. Y is a mess. Not too much of a mess, but it is the natural log of x raised to the x squared power. And this is my derivative. Recall that a huge part of calculus, at least the first half of Calc 1, is finding the equation of tangent lines. And the equation of a tangent line is going to be y minus y1 is equal to m times x minus x1, where this m is the derivative at x1. So we have this y is equal to x squared natural log of x, and we're looking at the point 1, 0. So this is our x1, y1, and we need to find the derivative of this function, and what that derivative is equal to at x1, so at 1. So let's take our derivative of y is equal to x squared natural log of x. So dy dx will be equal to, well, this is an x squared times a natural log of x, so we have a product. So that'll be the first function, x squared, times the derivative of the second function. The derivative of natural log of x is 1 over x, plus the second function, natural log of x, times the derivative of the first function. The derivative of x squared is 2x. So dy dx is equal to x, because these will cancel out, plus 2x natural log of x, and I could actually factor out an x, but, well, I'll do it. We don't really have to do it this time. So we have x times 1 plus 2 ln of x. And we're interested in this at x is equal to 1. So that will be 1 times 1 plus 2 times the natural log of 1. The natural log of 1 is 0. So this will be equal to 1 times 1, which is 1. So then we have y minus y1, so y minus 0, is equal to m, which is 1, times x minus x1, which is 1. Which just gives us that y is equal to x minus 1. And this is the tangent line at the point 1, 0 to the function y is equal to x squared natural log of x.